Okay, thank you for that introduction. My apologies for not being Karlheinz. I received his slide deck a couple of days ago. I think I understand most of his main points, but I doubtless cannot present them as well as he would. And there is a risk that this is being videoed and Karlheinz will watch this later. So Karlheinz, my apologies for anything that I missed that I should have mentioned or made more of. Just to warn you, I had trouble in my own session getting through my slides in the allotted time. Karlheinz has sent me 50% more slides, so I will try and pace myself accordingly. This talk is about neuromorphic computing, about past developments, and also what's going to happen through the rest of HBP up to 2023. The background to this is that neuroscience is a deep scientific subject, and in attempts to understand the brain, people have developed all sorts of instruments and mechanisms for doing this. This graphic shows the present set of instruments that are available to understand aspects of brain function, and the inset diagram shows you which of these were available in 1988. So you can see that quite a lot of techniques have been added to this picture. New techniques such as fMRI are telling us a lot about the coarser scales of brain activity, where the microstimulation is also getting at the lower levels. There's a whole lot of techniques going on in there. And we can also see in this graphic the scales that are of interest to neuroscientists as reflected by these instruments. On the scale of a millimeter, we start down at about a 10,000th of a millimeter, 100 nanometers, up to scales of the order of a meter, the full brain. And we also have time scales that go from a 10,000th of a second, so 100 microseconds, up to a million seconds, which is getting to the order of months. All these are of interest, so we have to cover a very wide range of scales, both spatially and in time. To give you some examples of how these are manifest in real life, here's a tennis player diving for a ball. It looks like a virtual ball, so he's going to miss it. But if you think about what he's trying to do here, tennis is a game that requires very rapid reactions and physical movement, but those gross movements are on the time scales of hundreds of milliseconds. They are controlled by events happening in the brain on time scales of milliseconds. And, of course, in order to play like a professional tennis player, you have to start young. And therefore, learning to play tennis is something which takes years. Again, if you're going to understand the brain, you've got to cover all this range of timescales. I always, I enjoy watching tennis, and I always think that the things the professional tennis players can do, well, they look pretty much nearly impossible. But of course, that's how the game is designed, right? It's a game to be played by humans, and so it's carefully designed to be right at the limits of what is physically possible for humans. And understanding how we can do those kind of things on the timescales required is a real challenge. Now, if we're going to build computer models to understand this, then we're in the realms of simulation. And we all know, and some of this links back quite nicely to my earlier talk, that for simulation, the place we start is with the standard Workhorse, the good general-purpose computer based on the von Neumann architecture. And the principles of that computer are that we have data and instructions stored in a memory. The memory's a set of pigeonholes addressed by location, and what the processor does is it works sequentially through the instructions unless an instruction tells it to do something different. And the memory and the computation in this model are physically separated. You have the processor on one side, the memory on the other. You have address and data buses that connect them, a few control signals. And what this leads to is what's been known for a long time as the von Neumann bottleneck. The fact is that the amount of stuff you can get across that interface is the thing that limits the performance of your computer, the performance of your simulation. Now, that performance has been improving, and here's a graph remarkably like one I showed you earlier, though it isn't in fact the same one. And this is showing, again, the number of transistors that we can put in a microprocessor, the performance of systems, the clock speed, the typical power, and a new set of points that weren't on my earlier slide, the number of cores that we can put on a chip. And if you look at this picture, the top line on a logarithmic scale is good old Moore's law. The data's a bit noisy, but the trend is clear. And that's a straight line, and up to 2010, continuing, and still continuing today. What's interesting, of course, is all the other lines have kinks in them. Something changed. And that change was around 2004, about 10 years ago. Progress in performance slowed down, progress in clock speed stopped, the power was held constant, and of course that's really the thing that's driving the other two. The power reached its limit, and therefore you couldn't push the clock up, and therefore you couldn't push the performance up. And the solution to this is in the bottom graph, where the number of cores per chip, which had held stably at 1 throughout 40 years of the history of the microprocessor, that suddenly turned upwards, and we start putting more cores on each chip. So that's the interesting area down there. And this leads us into the issue of parallelism. Now we've got multiple cores, we've got to use them. How do we build parallel programs that make good use of those multiple cores? And key to understanding the problem of running simulations on modern computers based on multiple cores is the concept of scaling. The parallel computing folk talk about scaling in two ways. They talk about strong scaling. If you have a strongly scalable system, then the idea is you can take your problem and you can take it from one core to many cores, and if you take it to n cores, it goes n times faster. It completes in 1/nth the time. If you can achieve that, then you've achieved strong scalability. There's a weaker concept of scaling known as weak scaling, and here the idea is if you have a job that you can complete in a certain length of time, if you make that job k times as big and run it on k cores, then if you can still run it in the same time, you've achieved weak scaling. And for many jobs, even weak scaling is hard to achieve, unless each of those k threads is completely independent. So if you have k different jobs you want to run, you can run them on k different computers, then they will run in the same time as a single job, and you can achieve weak scaling. But any single problem where there's interaction between the different components, even weak scaling is in general quite hard to achieve. And if you apply these concepts to the idea of using off-the-shelf computer technology, in this case a supercomputer, so it's a fairly big shelf, you have to get it off, but it's still a standard machine, and you look at what's possible on current machines, then you can plot the scale of the neural system that you want to simulate, and the speed at which it operates, and you can look at any particular machine and plot what's possible. And what this graph is showing is that if you take an off-the-shelf 10 petaflop supercomputer, which is fairly close to the top of what you can get today, it's not quite the fastest in the world. I think Tianhe 2 is about 33 petaflops. That's the supercomputer in Guangzhou in China. which is number 1 on the top 500 list. But what you can do with that class of machine is, with small neural systems, you can get close to real time. As you scale up the complexity of the network, you reach a point where you run out of compute, and then your speed relative to real time slows down until you reach the point where you run out of memory. And what you can do on a 10 petaflop machine sort of limits out at running something of the order of a mouse brain, quite a lot slower than real time. Now, these techniques are important, and they're widely applied. And if we look at the Human Brain Project as our local example, then using standard off-the-shelf supercomputers, what you can see in the project in different places are 2 different approaches. And these are characterized by previous work on the left-hand side in the Blue Brain Project at EPFL, where what we're trying to do is look at the structure of the brain, look at the structure of a neuron, and model it in very fine detail from the bottom up. So we're looking at physics-based models. We're working from first principles. The details of the model are all defined from experimental data, and then we can assemble this into systems, and we get a very high model complexity. And this is, I guess, epitomized by Henry Markram et al.'s recent paper in Cell, which presents a very detailed model of a cortical microcolumn at this kind of level. And then the behavior of that neural structure effectively is an emergent phenomenon from the physics and data that's put in at the bottom. So if you like, that's, computationally speaking, that's a kind of golden reference model. The other approach based on conventional supercomputers is exemplified by the kind of work done previously in the NEST initiative. And here, you look at the biology, you look at the function, and you treat the function as the target of the simulation. And so these models are based on observed phenomena abstracted into equations, and then the amount of detail you put into the model depends on what you're interested in, what your hypothesis is that you want to test. You generally keep the model as simple as you can, consistent with your objectives. So the technical terms for this are Occam's razor, or the KISS principle. Has everybody heard of the KISS principle? That's the polite version. The version I've heard is keep it simple, stupid. Keeping things simple is always a good idea. Composability sometimes suffers as a result of this. But there are these 2 approaches you'll see in different sub-projects within HBP itself. And what you can get with these, this example is work done by Marcus Diesmann at Jülich, and he was using the K computer at Riken in Japan, which is not a small computer. It's 12.6 megawatts of compute. I don't know where it is on the top 500 list. I think it was the top initially, wasn't it? Like most top-end supercomputers, they're top of the list for about 2 weeks, and then something else.
The lights go out when he runs the simulation.
Sorry?
The lights go out in the village.
The lights go out in the village, do they? Yes. Anyway, what this is showing is that as the network size increases, if you put more compute nodes in, you can keep a sort of fairly linear relationship between the network and the size and the amount of machine. Sorry? It's number 4 on the top 500 list. Right. So it's still pretty good. And by using more cores as the network size increases, you can just about keep the runtime constant, shown by the dots along the bottom. So what you're showing here is fairly good weak scaling. The resource is going in proportion to the problem. But basically, throughout here, the simulation speed is 1,500 times slower than biology. Okay, so relative to biology, you've taken a more than 1,000 times slowdown to achieve these results. This is using German notation for thousand separators, which confused me initially because in the UK we'd read that as 1.52 to 1. But apparently the dot is the thousand separator in German notation. And French. Well, probably everybody except the UK would. This would be normal. Runs on a big computer. Here's the K computer. It's a sort of aircraft hangar full of boxes, like most high-end supercomputers, simulating 1 billion very simple neurons on 65,000 processors. So it's 1% of the scale of the human brain, 13 megawatts, 1,500 times slower. If you do the sums for energy equals power times time, what you find is that this machine is 10 billion times less energy efficient than the biology at running this particular job. So what we find from conventional computing is on the scale of energy, and this is part of the graphic I showed you in my talk earlier, it's a subset of it. What you see is that the brain at the bottom here, using 10 to the minus 14 joules per synaptic connection, can be simulated on conventional machines, either in very high detail, in the blue brain style at 1 joule per connection, or more efficiently in the more abstracted point neuron style, using 10 to the minus 4 joules per synaptic connection. And so those two principles are 10 or 14 orders of magnitude less efficient than the biology for doing the same thing. And the question is there some middle ground? Can we find something that does this better? Now, where does this 10 to the minus 14 come from biology? Interestingly, you can approach it in 2 different ways, and you get the same answer, which is always reassuring. If you think about it top to bottom, take a whole human brain, about 20 watts, and in that brain you'll find there's the order of 100 billion neurons firing on average at about a hertz. So that tells you you've got the order of 10 to the minus 10 joules per action potential per spike. But here we're looking at a synaptic connection, so each spike goes to the order 10 to the 4 synapses, and so you get the result 10 to the minus 14 joules per synaptic transmission. That's the top-down approach. The bottom-up approach, which is based on the details of what's happening in the synapse, is it's been measured that you need about 10 to the 9 ATP molecules to be hydrolyzed for an action potential. ATP is the fuel for the biological system. And you need about 10 to the 5 to be hydrolyzed for a synaptic transmission. So what that tells you is that you get about 10 to the minus 19 joules. Separately you can establish that you get about 10 to the minus 9 joules per ATP molecule, approximately 1 electron volt. And so if you put those numbers together, that tells you get 10 to the minus 10 joules per action potential, 10 to the minus 14 joules per synaptic transmission. So the bottom-up approach gives the same order of answer as the top-down approach. And this 10 femtojoules per synaptic event seems to be a robust reference point. So what can we do with electronics? Okay, if we're going to build simulations in today's world, the best tools we have for doing this are all based on electronics. So let's take an electronic device. Here's a standard abstract model of a transistor. Pretty much everything today is built in CMOS, so we're talking about a MOSFET. And if we do the sums, looking at the size of the transistor and the voltage that's used to operate it, it's a very capacitive operation, so the half CV squared model gives you a good estimate of the energy required to switch a transistor. And if you do the sums, what you find is that switching a single transistor takes about half a femtojoule. Compare that with a synaptic transmission of 10 femtojoules, and what you see is that each synaptic transition in biology uses about the same energy as about 20 CMOS transistors. And so, in some sense, electronics is working in the same scale as biology in terms of the energy required to do something. A transistor is doing a lot less than a synapse. Is it doing 20 times less? It's probably doing rather more than 20 times. A synapse is probably doing rather more than 20 transistors, but it's that kind of order, okay? And so in electronics, we have something which is working at a similar efficiency level to the biology. So why are these computations so inefficient? What's happened between the basic device and the computation? And the answer is, of course, quite a lot has happened, and it's to do with the architecture of the machine that we use to engage these transistor switches and the computational model we use at the high end. So if you look at the structure of a chip is made of the functional devices are transistors, but as I showed you in the picture earlier, this is a similar picture. A lot of what you see on a chip is wiring, and if you look at the analysis of where the power goes in a chip, typically you spend about 1,000 times more energy in the wires as you do in the transistors. So we lost 3 orders of magnitude just in wiring the transistors together. And so we're now 3 orders of magnitude behind on biology. We're also using a machine that has not been designed specifically to model neural or synaptic processes. It's been built to do Boolean algebra. Okay, that's the basis of modern computers. Is everything is represented in binary, and the operations are all Boolean algebra. And mapping that back around to modeling the fairly continuous physical processes in the neuron and the synapse loses you quite a lot more efficiency. And so that's why you see this enormous energy disparity in practice between the biology and the computational model. The other factor here, of course, is that these simulations are running slower than biology. And what does this mean? Well, imagine you want to model the activity of a brain for a day on the K computer using the point neuron model computationally running at 1,500 times slower than biology. Then a day times 1,500 is about 4 years. Okay. So it's rather slow for some of the things you might want to do. Why do we want to model things that take a long time? Well, for example, if we want to model the development of the adolescent brain, why would we want to do that? Well, I guess there's a scientific interest in this. I think there are enough adolescent brains around. But, then, you're talking about 15 years of developmental change in the brain. And these slides are showing that when you make fundamental measurements on the structure of the brain, you see very significant differences over those 15 years. So there is clearly something important here to understand. And if you modeled 15 years using the K-computer approach, then that would take you 22,500 years of simulation. Is that right? Did I get that? I did that in my head. I think I got it right.
I'd like to see you write the grant proposal.
Yeah, yes. Well, for most scientists, results which are going to come 20,000 years after they've died are not very interesting. So, how does all this come together in terms of computation? Well, it is the case that neural modeling is quite a nice computational algorithm for scalability. And in fact, you can achieve strong scaling in quite a lot of circumstances. What resources do you need to model a range of brains? Well, the cellular neocortical column, which Henry et al. Published in Cell very recently, requires the order of 10 teraflops of compute and the order of a terabyte of memory. So that's achievable. If you scale that up, then you can draw a pretty straight line and say that the requirements will grow linearly with the neuronal complexity. And so you can reasonably get scalability out of that. But that may not be all you're interested in. This is just running the real-time point neuron models. There's more detail in the biology than those models capture. And for instance, if you want to add details such as the influence of vasculature or glial cells, then you can expect your simulation cost to go up by 10 times. If you want to model it using reaction diffusion models, so that you're modeling the sort of physical movement of the chemicals in the brain, then you can expect the computational cost to go up by 2 or 3 orders of magnitude. If you want to model it at the level of molecular dynamics, then it's going to get 1 billion times more expensive. So if we can get to simple models of the human brain with an exaflop, we still have another 9 orders of magnitude beyond that before we get to be able to model the brain at the level of molecular dynamics. If you add plasticity to your model, then you can expect an order of magnitude increase in computational cost. Learning, which takes time, is 1 to 2 orders of magnitude, and development, the teenager to adulthood model, is 100 to 1,000 times more complex in computational terms. So if you want to go below the sort of cellular model, then that kind of detail requires significant advances in strong scalability. What do these numbers mean in terms of timescales? So taking the 1,500 times slower, if we're looking at causality detection, which may happen in the 10th of a millisecond, the simulation will take a 10th of a second. Plasticity goes from a second to 1,000 seconds, which is 20 minutes. Learning, which takes a day in nature, will take 1,000 days, several years in simulation. Development, which takes years, will take 1,000 years. And of course, if you really want to look at the long term, then you can model the evolution of the brain structure. And then in nature, evolution, well, it says millennia. I think that's probably a lower bound to evolutionary phenomena. And you're talking 1 million years to capture that kind of thing. There's a Feynman quote. Karlheinz is a physicist, and so you have to quote physicists. And Feynman proposed this rule of simulation, is that what he would like to see is that basically the number of computer elements required to simulate a large physical system is only proportional to the space-time volume of the physical system. So if you want to double the volume, you want it to use double the resource, not something that's exponentially larger. So again, he's talking about linear scalability of the compute problem. Now, this talk is about neuromorphic computing, so it's time we mentioned it. The idea of neuromorphic computing is to try and fill in some of the gaps in that energy scale. And the key concept in neuromorphics is that we will implement some aspect of the thing we're trying to model, the structure and or the function of biological circuits, and we'll implement those in some analog or digital form on electronic substrates. So we'll take some part of the problem and map it into the physical structure. And that's the neuromorphic aspect of the systems. And these may be cell cores, networks, connections, or it may be function, so local processing, communication, or dynamics. And a number of groups are doing this on a large scale, which is the focus here. If you look at one way of approaching it, I've described earlier the Spinnaker system, which uses commodity microprocessors And here, the neuromorphic aspect of the system is the way we've built the interprocessor communication. So it's the communications that are neuromorphic, the rest is conventional computing. And that work is now going on within the HBP. A fully digital implementation has been built by IBM. This is embodied in their True North chip. And there they've reduced the flexibility, so they've fixed a whole lot of functions into the hardware, and that allows them to get much larger neural systems onto the same piece of silicon. And the third approach mentioned here is the mixed signal approach, full custom, and this is epitomized by Karlheinz's earlier work in brain scales, which again is now supported within HBP. And within HBP, we describe Spinnaker as the many-core neuromorphic system, and we describe brain scales as a physical model. It's mapping more of the physics of the model into the hardware itself. There is, of course, in the wider world, there's a bit of a debate as to whether an approach like Spinnaker is actually neuromorphic at all. The original definition of neuromorphics from Carver-Mead was much more focused on the analog circuits, which behave like the biological circuits, and Spinnaker doesn't do that. But at least within HBP, we group these together under the neuromorphic heading. These are all different approaches to the same problem, so you'd expect they have some things in common. And one of the things they have in common is they're all massively parallel. So they have much greater degrees of parallelization than most standard computer systems. And they all deliver something that's close to perfect weak scaling. What that means, if you remember, is that if you want to make your model twice as big, you just get twice as much resource and it'll go at about the same speed. So on Spinnaker, if you have twice as many neurons, you need to use twice as many cores. On True North, if you run out of one chip, you double your model, you need 2 chips. And similarly on the physical model. Another thing they have in common is asynchronous communication. So if you look at the brain, what appears to be happening is neurons are mainly communicating with spikes. The spikes happen when they happen. They're not synchronized to a clock. There are, of course, rhythms in various parts of the brain which have some clock-like properties. But all these systems treat spikes as individual asynchronous events that get communicated. They happen when they happen. And the third feature is configurability. We're all aiming to be able to model many different brain areas. So we don't hardwire a particular cortical microcolumn structure or anything into the way the system is built. That's part of the configurability. If you want to model cortical microcolumns, you can do that. If you want to model cerebellar connectivity, which is quite different, you can do that just by changing the configuration. And they all represent trade-offs. I mean, this is a fundamental thing you have to understand about neuromorphics. There's always a trade-off. If you want complete generality, then you want to use a big supercomputer where you can do anything you like. There's a trade-off there, it won't go as fast. But a typical trade-off in these neuromorphic systems is that, to some degree, the flexibility and complexity of the neural model has been restricted in some way. So Spinnaker is tuned to point neuron models. Because the model is software, you can do other things, but if you do other things, you find the architecture balance is less good. And the same is true in True North and in brain scales. In fact, the neural model is pretty fixed in both cases. So they all present complementary approaches. They all contribute, and they're all useful for different things. So if you're looking for a neuromorphic platform to do something on, you need to go and look at the various choices out there and see which one is better suited to your problem. And of course, I've mentioned 3 of them here. There are a number of others not mentioned here. So in HBP, we have two of those three, and these are quite different approaches, quite complementary. The many-core system is the order of 1 million ARM processors. We're committed to delivering a 500,000 core machine to HBP, but our internal objective is to go to double that. The key features of this is that the communication is through a packet switch network, but it uses tiny packets, and it's scaling down packet switch communication to the scale of having a router on each chip. That is the key to the way Spinnaker operates. And it runs in biological real time. That's the goal. It's not fixed at that, and in particular, if it runs in biological real time, if you use millisecond time steps, if you want to go to sub-millisecond time steps, you probably want to scale time a bit. But nominally, it's about real time. The physical model system at Heidelberg uses analog models of the neurons and the synapses, and they can compute 4 million neurons, 50 million synapses, and it runs 10 to the 4 faster than real time, okay? So unlike the supercomputers, which can't do real time, they're slower, the Heidelberg system is quite a lot faster. And that's because if you map the neuronal equations into analog electronics, if you do it in a standard approach to analog electronics, it's very hard to get it to go slow, okay? Now, there are advantages in being fast as well, but actually it's more efficient to build a faster than real-time system in analog electronics. We'll talk about the pros and cons as we go through. So here's Spinnaker. I talked about this earlier, I don't need to say much more now. We have lots of cores. They run at 200 megahertz, so they're running at a modest speed. And they have memory on chip. They have a bigger memory within the package, so we're using basic 3D packaging here. And each chip has 6 connections to its neighbors, and those connections will convey up to 6 million spikes a second. And it runs in real time. The core of Spinnaker is the packet router, so the rest of it's conventional software. We run neural models in software, synaptic models in software, so if you have a new plasticity model, it's a little bit of C code. A new neural model, it's a little bit of C code. It has to be written quite carefully because it's real-time code. But then what those models do is they receive spikes that come from elsewhere in the network, and they send spikes that go elsewhere. And all of this is integrated in a tool flow that makes using it fairly simple. If you've written Pine to run on Brian, there's a reasonable chance your model will simply run on Spinnaker by changing the back end. And at the heart of this is a router, and this is a packet switch router, so it's doing the same job as the 1U 19-inch boxes you see in all the machine rooms with all the Ethernet cables going in. But here it's doing it in a few square millimeters of silicon because it's all been scaled down and made very lightweight, and the packets are very small. If you look at the chip itself, it's got a bunch of processors there in the blue area. I might actually use a pointer here. Does it work? I might use it if I hold it the right way around, it might work better. Yes. Yeah, so the processor's somewhere in there. There's other stuff. It's all compiled by a synthesizer, so it's completely unrecognizable to humans. The processor is integrated right next to its instruction and data memory. Remember my principle from earlier, energy equals number of bits moved times distance. This is about as short as you can make the distance. It's about a millimeter. And all the frequently accessed code and data lives here for this processor, and you can see that repeated 18 times across the chip. Less frequently accessed stuff, and this is typically the synaptic connectivity matrices, get exported through this shared RAM port to DRAM, so they're about a centimeter away from the processor. And in the middle, this red square is the router, which is if you like, the innovative bit of the whole architecture. And because neurons are highly connected, each neuron connects to 10,000 others on average, we use a source address-based multicast routing system. So when a packet's transmitted, it's like AER, address event representation. All the packet says is where it came from, and the router has tables that determine where it goes to, and that may be many places across the system. The overall machines above a certain size are folded together as toroids. It's basically a 2D mesh with periodic boundaries. And then we fold these up to form the machines. And there are multiple paths available within the machine. There's at least 2 and usually 3 routes you can take to get from anywhere to anywhere else. And the whole thing's designed so that you can get stuff around the machine in a small fraction of a millisecond. So that's what we mean by biological real time, sending a packet from a processor anywhere on the machine to processors anywhere else in the machine. The latency there is a small fraction of a millisecond, typically a few tens of microseconds. And we've built machines. You saw these earlier. The biggest machine that's running is the 105 with 100,000 cores, about mouse brain scale. Again, remember, simple abstract point neuron models. And Karlheinz describes this as a drastic approach to weak scaling. I've not quite worked out how to translate that from the German. True North is the IBM design. It's quite interesting that you know, there's 2 academic groups mentioned here and one of the world's biggest computer companies. It's taken us all about 10 years to build these machines. So you might expect a big company to do this much faster, but the 10-year timescale seems to apply whether you're a small academic group or a large company. And the IBM chip is a very aggressive digital design. It's done on 28 nanometer process technology. They get 1 million hardwired LAF neurons on a chip. Each of those neurons has 256 inputs. The inputs are arranged in a crossbar, and basically you have a single bit, a binary bit, to connect or not connect, with some global scaling on each row of the crossbar. And it's the biggest chip IBM's ever made, interestingly, 5.4 billion transistors. One of the limitations that results from a binary synapse is you can't implement real-time plasticity on the chip itself. All the learning you have to do in an external computational model before you load the model onto the chip for real-time operation. The True North runs, like Spinnaker, at biological real-time speeds. The third system, Karlheinz's system, is a physical model, and here the idea is that you look at the equations that describe a neuron, and you look at electronic analog circuits which implement the same equations. If you know digital electronics, you will know that to multiply 2 16-bit numbers in digital circuits takes an awful lot of transistors. You basically have 256 multiply elements wired together. If you translate those into analog circuits, you can do a multiplication with a couple of transistors. So there are real efficiency benefits in implementing these circuits in analog ways. You will, of course, not get the full 16-bit precision if you implement it in analog circuits, but arguably that really doesn't matter for this kind of modeling problem. If you look at the fundamental time constants at work in the electronics and compare them with biology, then you'll see why we end up going faster than real time. So this table along the bottom here, voltage changes. VLSI circuits tend to run in the order of, this says 100 millivolts. Biology is a tenth of that. Leakage currents, there's 2 orders of magnitude difference. Membrane capacitances in biology are quite high because of the way the lipid membranes are formed. In electronics, natural capacitance values are 3 orders of magnitude smaller, and that's really where the speed difference comes from. And so if you work out the natural speed, the G delta V over C in terms of volts per second, then you see there are 6 orders of magnitude difference. And that leads you towards running the electronic analog at higher speeds. And the time is determined by the physics of the circuit, not by any external system. So if we look at the chip itself here, the basic chip is 5 millimeters square. With that, you get 100,000 dynamic synapses. And if you look at the circuit layout, what you see is with order 256 or 1,000 synapses per neuron, then the synapse circuits dominate the chip. The neural circuits basically are tiny because numerically they're far fewer. And so the neuron density is not what matters, it's the synapse density that affects the outcome. The way the chip works, it's mixed signal, which means it's got both analog and digital aspects. All the computation is analog and local. And then you have communication, which is done digitally, a bit like the brain. If you think about the pulses flowing in the brain uses the reliability and the noise resilience of digital communication to send signals between neurons as spikes. And the same thing is happening on these circuits. We're going digital. We can also then use efficient digital circuits for switching and for the configurability. And I think on the latest version of the chip, there are actually software elements which are involved in the local plasticity as well. So where plasticity comes in, the latest version is using digital approaches. This started in the BrainScales project, where the HiCAN chip was developed, where HiCAN stands for High Input Count Analog Neural Network. And these chips were produced some time ago and have been in use. This is now being scaled up to full wafer scale, so to get the large-scale circuits encompassed by the system, the Heidelberg group is going for full wafer scale integration. Now, wafer scale is extremely challenging. Building these things is new territory. But this allows them to build 200,000 neurons and 50 million synapses on a single 8-inch wafer. And within this, they incorporate short-term and long-term plasticity, and they're running 10 to the 4 times faster than real time. What they're yielding is a big machine, shown here with a human for scale comparison. So again, its physical size is similar to the million-core Spinnaker machine. It's basically built in full-height 19-inch cabinets, and it uses, well, I can see about 7 in this picture. So it's a big machine. At Heidelberg, there are 4 million neurons in total on multiple wafers, 1 billion conductance-based synapses, and it runs fast. And this and Spinnaker are both accessible through the HBP co-laboratory, it's called this week. And you can upload jobs and run them on either or both of these machines, and at least one person in the room has used both. Isn't that right? Yes. Hold your hand up. This man has used both HBP platforms, so I don't, are you the only one? So he must be the hero in the room. If you don't need a big machine, if you want to do some early scale development, then there is a small version with the spiky chip, which is a USB powered laptop. And this has software support and documentation. With that, you get 498 neurons and 100,000 plastic synapses, and that's 10 to the 5 times faster than real time. So it goes even quicker, and it comes in a neat portable box. Just to mention that there is a similar small Spinnaker development system, probably in a very similar size box that you can also power off USB. So both of the HBP platforms have sort of small development kits plus large machines based in Manchester and Heidelberg. So, what are these giving us? Well, the neuromorphic systems actually serve two roles in HBP, one of which is the kind of thing we've been working through, which is computing for neuroscience. How do you build your neuroscience models and get them to compute in sensible times? But there's also the other side, neuroscience for computing. What can we learn from neuroscience and take back to build better computers? And as a neuroscience research tool, we can select the execution speed. If you want to model development, then the Heidelberg system will speed you up by a factor 10 to the 4, which is very useful if you want to model 5 years of development. If you want to interface your network to a robot, then real-time is probably more like what you want, and Spinnaker may be more suited. You can get to grips with a very wide range of timescales, and you can look at multi-scale theories and verify or falsify them. We also get a novel computing architecture, and these architectures are delivering low power, scalability, speed, fault tolerance, learning, and so on, which are all innovative features in the computing sense. And you know, they're likely, because they're neural networks, to be good at processing noisy and random data. And they may be applicable to data, biological data, but also non-biological data. And in fact, you know, with Spinnaker, we have users who are using Spinnaker to process big data from all sorts of random sources. One of the challenges, we're aiming in HBP to build these big platforms, but one of the challenges is to understand how best to downscale this. How do you make these things small enough that they can deliver the results of neural computation into your smartphone, for instance? Qualcomm has their zeroth accelerator. What can we do that's similar to that? And there's the potential to use these kind of systems to build demonstrators for novel devices. Some of the discussion earlier on memristors might be an example here. What kind of things can you do with them? Well, there are four main categories of experiments and applications. You can look at properties of isolated cells, firing patterns, and so on. You can look at circuits, reverse engineered into some kind of closed loop form. You can build theories and implement networks to test them. And then you can build controllers for applications outside neuroscience. So if we look at examples of the first one, you know, what's a typical kind of circuit that people tend to build to get something going? Well, a fairly common circuit, it would be something like a SynFire chain, where you propagate a synchronous wave around a network of neurons. And this has been done on the analog system. It's also been done on Spinnaker. At a larger scale, you can do something like build a model of the rat barrel cortex, and Tom Sharp's paper on this claimed to be the largest network ever simulated in real time. In the second category, if you're trying to build things into closed loops, then quite often this means some kind of robotics platform gets linked in here, and Spinnaker is being connected into the TU Munich robotics platform built by Jörg Konrad, and it's got vision sensors on this from ETH Zurich. And these vision sensors are event sensors that generate spikes, and so you have a network that then runs control algorithms and causes the robot to do things. I remember one of Francesco Galuppi's demonstrations was a robot which had a concept of there was cheese here and there was home here, and you could fertile with its basal ganglia to decide whether it wanted more to eat cheese or go home. This is probably the most complicated way of getting a robot to go from A to B and back again that's ever been invented, I think. You can build more biologically realistic circuits, and IBM have published papers looking at the insect sensors and building models of that. And this, I think, is the model that they built. which has all sorts of curious symbols in it that I don't particularly recognize. And they can assess this and see if they can reproduce the characteristic behaviors and properties of the insect system. This is the olfactory bulb glomerular layer computations. Olfactory, I think, means smell. And related things have been done on the brain scale system, 3-layer networks, decorrelation through lateral inhibition, and so on. Are you looking agitated? Yes, okay. Lunch is at 12, is it?
Midnight, perhaps.
It's all right. I told you Karlheinz had far too many slides. I've only been talking for 54 minutes.
Well, we just thought you needed some early warning to stop.
This is demonstrating data classification, again running on the Heidelberg system, and classification performance compared to software. It's all doing very well. Okay, so I'll skip through these a bit. If you're looking at devices, here's an exciting device, and here's some graphs showing variable classifiers. Yes, I'm sorry, I'll get through this if you want me to stop. Testing fundamental generic concepts and theories. You can start with the usual sort of visual conflict. Do you see a duck or a rabbit? This is an old one. Apparently you can see both ducks and rabbits in this. This is an old example. And you can build networks that try and demonstrate the ambiguity in that picture, starting from the input pattern. You can build a deterministic network that generates an output pattern, or you can build a stochastic network, and with these you can illustrate the ambiguity in the pattern in an artificial network.
I should say, by the way, that's the link to the theory subproject, which dealt with an earlier meeting about, I think it's on Friday. So there's a link, that's why that's there. Boltzmann Machines the theory side.
This is Boltzmann machine. Yeah. There's a lot of interest at the moment in Boltzmann machines, of course, because restricted Boltzmann machines are the basis of the deep learning networks, which is getting all the machine learning community extremely excited and extracting hundreds of millions of dollars from Google for various purposes. And on a much smaller scale, there's quite active interest in understanding how to build these kind of deep learning systems using spiking neurons, and some evidence that spiking neurons are quite good at this, although it's early days yet. And I don't think I'll try and explain that one. If you look at membrane potentials of two non-stimulated ADEX neurons on the HiCAN chip, then what this is measuring the variability. It's one of the issues with analog electronic circuits, is getting them to perform consistently is difficult, and the performance maps have been produced to analyze these variations. Balanced random networks are the sorts of things you can model, build models such as the one on the left, get raster plots, and again, this has been reported in a published paper. Here's a bunch of lift neurons, sampling states. Again, this is in Michal Petrovic's PhD. Is Michal here? I'd invite him to explain this if he was. Boltzmann distributions over random variables. And I think, where am I getting to? Oh, I think we're almost at the end now, don't panic. And then pattern recognition. This is looking at handwritten digits. looking at local interactions, the network on the left with no inputs is free running and it's basically dreaming all the different digits it's learnt. The network on the right is given some input and it infers that that input is more compatible with the 0 that it's learnt than with the 4 and the 3. So basically what we're doing with the neuromorphics in HBP is filling the gap in the picture. Instead of having the choice between biology and then 10 orders of magnitude gap up to computing, we have options now that run at 10 to the minus 8 joules and 10 to the minus 10 joules per synaptic event. So they're much more efficient than conventional computing. They're still less efficient than biology. We can't compete with biology yet. So they fill an important gap in the set of options available to people who are wanting to do computational neuroscience in some form or another. And what they give you is the ability to also fill in on the timescales. So if you look at the natural process, the simulation time on a computer, and the accelerated model, then what you see is we've got many orders of magnitude of range improvement by using the accelerated system. In HBP, there's a roadmap. We are developing Spinnaker 2. We have the first test chips, not in our hands, but in the hands of our collaborators at Dresden. And we are planning to build a machine that's roughly an order of magnitude more capable than the current machine on the timescale of about 2020. And the same is true with the Heidelberg system. There they have plans to build 2 further generations within HBP. And again, they have interesting developments on the route to get there. The model we're trying to follow here is the idea of constructing concepts which will prove generally useful over time. The base technology may change. Just like with the original computer, early computers were built with vacuum tubes and delay lines and cathode ray tubes and so on. They've all gone. But the key idea is the memory processor von Neumann architecture, the universality, and the scalability have allowed that model to persist to today. And the goal is to try and find the equivalent neuromorphic model. What is it you can do in neuromorphics that will stand the test of time? As technology changes, it'll still be a useful model into the future. And so my last slide, you'd be pleased to know, is talking about using this approach to develop a consistent set of concepts for brain-derived computational function. And it's the only approach that we're aware of that can bridge all the timescales relevant for the dynamics from milliseconds to years. There are 3 major large-scale systems around the world, two of which are supported in HBP. Key features we're aiming for are universality, scalability, fault tolerance, power efficiency, speed, and learning. And just to emphasize, these are not going to replace traditional computing. Traditional computing will continue and probably dominate, but they are supposed to fulfill a gap in traditional computing when it comes to cognitive systems and machine learning-based systems, where these will significantly increase the capabilities in those domains and allow lots of new applications to be delivered of value to humanity, we hope. So, thank you very much. That's the end of the talk. I'll stay being Karlheinz for questions, although that may be even more difficult than delivering his slides. But I'm happy to try. So thank you very much.